Okay, this is 1987. I don't even know if you can get to answers on these online anymore, but give it a shot. Um, so it's a 1987 AP Chemistry for Response question, and the equation for the above reaction between mercury 2 chloride and the oxalate ion in hot aqueous solution is shown above. Oops, I got to see if I can get this. Um, The reaction rate may be determined by measuring the initial rate of formation of the chloride ion. Interesting. You have to pick a product and just one. They are choosing to monitor how fast this is produced. You could also do how fast this was produced or how fast this was produced, but for some reason, there's something in the experimental process that this is the one that makes sense. Um, for various initial concentrations of mercury 2 chloride in the following table. And then I'm just going to go back here and write the rate law expression for the above reaction. So just to do a little bit of review, I'm going to flip back and forth, but so to do a little bit of review, remember now the rate law is equal to, sorry, the rate of a chemical reaction is some, this is called the rate law constant, um, and it changes for temperature, and so what you have to know is that tied up in this K is the temperature. Generally, as the temperature goes up, the reaction goes faster, and K gets bigger. As the temperature goes down, the reaction goes slower and K gets smaller. But the temperature, which affects reaction rate, is all tied up in K. But if you go back, as I flip back and forth, the reactants are HgCl2 and the oxalate ion. This must be a net ionic equation. And so what happens is we know that the first reactant's name is HgCl2, and we need to figure out what its order is. And then we have the oxalate ion, and we need to figure out what its order is. Sometimes I do this, sometimes I grab this eraser, and I change these over to x's and y's, like what's, I'll call the power of this x and the power of that y. But the that's interesting about the rate law, oh, that sounded really stupid, I'm sorry. The thing that's interesting is the only thing that goes in the rate law is the concentrations of the reactants. And it's the initial concentration of the reactants, because as the reaction proceeds, the reactants are slowly turning into products. And as this goes away, the concentration is dropping, which is going to make the rate drop. So we always just monitor at the very beginning, and we measure the rate at the very beginning, and then we stop, and then we switch the concentrations. So now I have to go back to the table, because to find the order, and the beauty of the smartboard is I can switch colors. To find the order of HgCl2, I want to change the HgCl2 concentration and leave this alone. And so for me, it makes the most sense here to do um, trial 2 and 3, and then trial 2 and 3, and then trial 2 and 3. And so that's red. And so when you do the later trial divided by the earlier trial, this 0.404 divided by itself is 1, so there's no change here. 0.4018 divided by 0.0836 is approximately, because there's experimental error, 0.5. And we're trying to figure out what the order is. And then I don't know what 1.06 times 10 to the negative 4. You can do a calculator if you want. I always do the later trial divided by the earlier trial. But the interesting thing about doing it this way is this 10 to the negative 4 cancels with this 10 to the negative 4, and 1.06, 1.08. This is pretty close to 0.52. 0.5 also, I guess I should say. So 0.5 to what power would give you 0.5? And going back, or going forward to this slide, is I now know that this is 1, because 0.5 to the first power would give me 0.5. All right, so now to go back and get the oxalate, well, to figure out what the oxalate is, and I'm going to do purple this time, you're going to change the oxalate, but not change the mercury 2 chloride. And in this sense, it makes sense to do this one, because 0.0836 divided by itself is 1. The ratio is 1, or no change. This, it doubles, because 0.404 divided by 0.202 is 2. And here, I have to get a calculator out, but if you get a calculator out and you do 2.08 times 10 to the negative 4 divided by 5.20 times 10 to the negative 5, this ends up being approximately 4. So now the next question is, 2 to what power gives you 4? Well, what does y have to be? Y has to be 2. So I'm going to come over here and I'm going to cross this out. And now this is going to be a 2. And so going back to the original color, the rate law expression, and the expression is what it's called before you usually solve for K, is it some K, which we don't know, it's a constant, it's the same number unless you change the temperature. And then we know that HgCl2 is first order, and I'm actually going to put the 1 in here, and then times, and then the second order with respect to the the oxalate ion. So this is a 2, so this is the answer for A right here. Then B says, calculate the numerical value of the rate constant and specify units. So if I take my answer for A, which is rate equals K times the concentration of HgCl2 to the first times C2O4 minus 2 to the second, and we solve this for K, we would divide both sides by the same thing, because this would cancel this, and then this would cancel this, but there's a rule in algebra that whatever you do to one side, you have to do to the other. And I'm being very long-winded. Most of you who are in multivariable calculus or calculus BC probably don't need to see me do the algebra, but the way you solve for K is you take the rate of any trial, and I'm probably going to use trial 1, and you divide it by the concentration of HgCl2 to the first power and the concentration times, this is supposed to be a times, C2O4 minus 2 to the second power. And so if I go back to my chart, I will see that the rate for trial 1 was 5.20 times 10 to the negative 5th molarity per second. And then the concentration is downstairs, so I'm going to multiply by the reciprocal, and this is 0.0836 molar. Now I'm going to do something, this works better with my college prep kids. I don't notice that it works better with you guys, the AP kids, but here's the deal. Doesn't squared mean it gets multiplied by itself twice? And so sometime, because of the whole unit thing, instead of squaring it, I will just write down the concentration of the oxalate ion in trial 1 down twice, because that's what squared means. Because or you can write this, but the thing that I noticed is that if I write it down twice, there's a smaller probability that you will forget to square the 0.202 and that you will forget to square the meter. So what happens is this cancels this, and when you do 5.02 EE negative 5 divided by 0.0836 divided by 0.202 divided by 0.202, my calculator says that K is 2.60 times 10 to the negative 4th. And an interesting thing happens. Let me toggle down here. all the units on the top cancel, and then we have two M's downstairs that don't cancel, and a second downstairs that doesn't cancel. And so this ends up being, I lied, that's not the answer. This ends up being, I was looking at the wrong one, 0.0152 over molarity squared times seconds. Or if you prefer scientific notation, 1.52 times 10 to the negative 2 over molarity squared times seconds. So that's K. And then what is the numerical value for the initial rate? This is a very tough question for my students every year. Okay, so listen, we are asking for the rate of disappearance because the the reactants disappear and the products appear. So what is the initial rate of disappearance of C2O4 minus 2? Now, I'm asking about the rate of C2O4. If we go back to the beginning slide, you don't know, you only know the rate of the appearance of this. You don't know, and you know the concentration. Now you got to understand that concentration and rate are not the same thing. And what happens is this is a very, very easy problem if you remember that the rates are connected by the stoichiometry. So again, at the very top of the problem, it says 2HgCl2 aqueous plus C2O4 minus 2 aqueous goes to 2Cl minus aqueous plus 2CO2 gas plus Hg2Cl2 aqueous. Now the interesting thing is, in experiment 1, I'm going to go back, and I'm looking in the rate. In experiment 1, the rate of formation was 5.20 times 10 to the negative fifth. So the rate of formation of Cl minus, and this is not a tough question once you get what it's asking, because it's all about stoich. So what they tell you is, in experiment 1, the rate of formation, or another way of saying that is appearance, not disappearance, because as the reaction proceeds, the reactants disappear and the products appeared. Well, they told you that the rate of appearance of Cl minus was 5.20 times 10 to the negative fifth molarity per second. Well, you can see, I'm going to switch colors, that there is a 1 to 2 mole ratio. In other words, this is appearing twice as fast as this is disappearing. This would be disappearing at the same rate as this because this and this match, but this is 1 is half of 2. And so once you understand that the rates are connected by the stoichiometry, the answer to this problem is 5.20 times 10 to the negative fifth molarity per second divided by 2, because it's appearing half as fast. And so then 5.2 times 10 to the fifth, half of 52 is 26. So this would be 2.6 times 10 to the negative fifth molarity per second. I think the way I usually teach this, okay, now this is June, and I'm not actually doing this, teaching this until late September, early October. But I told the kids, you guys, to set up a proportion like this. So grabbing the pen, and I'm going to do purple. 2 is to 1, because there's 2 moles of Cl minus for every 1 mole of C2O4 minus, as 5.20 times 10 to the negative fifth molarity per second is to x, because we're setting up a ratio. It's a 2-to-1 mole ratio. And so if you do this, you would get 2x equals 5.2 times 10 to the negative fifth, and then 2x equals 5.20 times 10 to the negative fifth molarity per second. But then you're solving for x, so you end up dividing by 2. However you do it, the answer is 2.6 times 10 to the negative fifth molarity per second. However you do that, there's a lot of number sense in AP Chem. And then finally, question, oh, I don't know, I think I got an extra slide here. And then I think the last question, D, which I don't know where it is, so let me just, because I want to do this. D, it says, calculate the initial oxalate concentration in experiment 4. So what is this concentration initially in experiment 4? And this is interesting because I'm going to do some algebra here. We know from part 1 that the rate is equal to 0.0152 over molarity squared times second times the concentration of HgCl2 times the concentration of oxalate ion squared. And so now in this question, they want us to calculate this, because in experiment 4, we know this, and we know this, and what we don't know. So the first thing is, just doing the algebra quickly, C2O4 oxalate ion concentration squared, because it's second order, would be calculated by taking the rate divided by K, which is this, divided by HgCl2 squared. But we want, and then what's the only thing in all of math that undoes a square is the square root. And so doing the algebra first, although you don't have to, because in kinetics you don't have to use the factor label method, but the C2O4 minus, sorry, the oxalate ion concentration is found by taking the square root of the rate divided by K times HgCl2, not squared. That one's to the first power. And so what happens is, if you go back to the table, I just want you to know where we're getting these. You know the rate, you know this, and we're solving for this. So what we don't know is that. And so what happens is, okay, I'm going to hit extend page. And so what happens is the rate was, pen please, 1.27 times 10 to the negative fourth molarity per second, because that was the rate for experiment 4. And then because K is downstairs, I'm going to flip it over. So I'm going to put the 0.0152 here and the molarity squared per second here. And then 1 over 0.0136 molar. And what happens is this cancels this, and this cancels this, and we have the square root of m squared, so that you can see that when you pop that into the calculator, you will end up with 0.0514 molarity. So apparently 1.27 times 10 to the negative 4 divided by 0.0152 divided by 0.0316, and then taking the whole square root of that whole thing ends up being 0.0514.